last 2 weeks we talked about gravity, we talked about light. Those are two of the main ingredients in how we understand our universe. And then there's sort of like that third ingredient, the vast scales of everything. If you sort of look at the stars, it feels like they're not that far away. And if you watch any science fiction or read any science fiction book, it's always like, and then we move to the next place, right? I remember seeing one of the latest Star Wars, where they just bump from, or I don't know, some science fiction, but they bump from one planet to the next. Because all the empty space is boring, but there's sure is a lot of it. And so the scales of it, the scale of our universe and the distances are the last part of the thing that we need to understand before we go into detail. And so cosmic scales, how to measure distances, is I'm dedicating a week of that because it'll keep coming back that we have to realize, oh, now that we know the distance, now we know everything about it, because we've measured color, we've measured how bright it is, and we've measured all kinds of things, but we didn't know how far that star was. So actually figuring out the scales of things was a big challenge for 19th century astronomy, because basically they didn't know how far things were. So you kept having these discussions of, is that fuzzy thing, is that part of our Milky Way or not, right? That's a big difference if it's in here or not, in our Milky Way or not. So we're going to talk about distances today, apparent and absolute magnitude. This is one of those things that we've inherited from the Greeks, that yes, we ended up with magnitude being our main measurement of brightness and therefore also distance. So apparent, how bright it looks to us, and absolute, how bright it intrinsically is. I'll talk about something called Cepheids, which are a very particular kind of star that we've used for distances. And I talk about the distance ladder, right? So how do you measure distances? Because can't go out there, can't go bring a measuring tape, so how do we do that? Part of that is that if you're talking great distances, you're also talking long time scales, long travel times, so to speak, right? So if you're talking, well, that supernova just ejected a whole bunch of metal and like iron and oxygen and carbon and whatnot, and so those are the building blocks of life. Yeah, but by the time you have to then get it to the next star, which will take millions of years because the distances are so long. So just to reiterate, we had Kepler's 3 laws, like these are planetary orbits, these are all planetary scale, so like years, decades, maybe 1 or 2 on a century scale. And so the fact that you sweep out the same amount of area during their orbit, and that the period and the major axis relate as the period squared goes as the major axis, or the major axis cubed. We talked about Newton's law of gravitation and the fact that we had tides coming out of that, right? The fact that you have if you have a difference in forces because the thing that you're looking at is not a point, right? So now we're going to talk about the scales of our universe. And yes, on Thursday, when I have Drew with his command of the dome, we'll actually work on this during the dome as well, but this will have to do for now. So scales, 10 centimeters, person size is a meter size, yard size is 10 meters or more. 100 meters is sort of like a quad at Google there. You go to 1 kilometer, that's the entire campus. Tens of kilometers, that's the entire area. And 100 kilometers, that's sort of like California size. 1,000 steps of 10, right? 1,000 is like all of the western United States. 10,000 is already our Earth. 100,000, the moon's orbit. Another steps of 10, like a million, the Earth system. 10 million, there's like there's the inner solar system. 100 million is the inner solar system. A billion is we get the outer solar system. It's distracting. There's a little bit of music playing here, but not loud enough. And so every time you do another step of 10, like another part of the solar system comes in, and 1 light year essentially is the width of our solar system. Another 10, we already have the first neighboring stars. 100, that's already a lot of them. 1,000, that's all the ones that we can see. And then 10,000 ones, we're now talking a spiral arm. We're actually rapidly 10,000 light years. It's going so fast because I'm taking steps of 10. Right, so that's what I'm trying to show you. And there recedes the Milky Way with our local group, and actually that's 100 million light years, 1 billion light years. I'll play this again because I really can't talk fast enough as we do steps of 10. Right, so now we're going the other way, right? We're doing steps of 10 closer, but even faster than anyone can talk. And so as we go steps of 10 into our solar system, steps of 10, steps of 10, there's our planet, and there she is again. Anybody getting vertigo? I am. And so we can do steps of 10 closer, right? 1 centimeter, right? So the size of your eye. 1 millimeter, the size of your retina. 100 micrometers, that's the size of the little capillaries in your 10 micrometers is a red blood cell. A micrometer is sort of the DNA strands in that blood cell. 100 nanometers, that's the width of one of those. You go down to 10 nanometers, 1 nanometer, honing in on like 1 atom. There's the electrons around that atom. And here's a great big nothing, a picometer, and then 100 femtometers, 10 femtometers. There's the nucleus. And this is sort of getting down to the smallest scales that we know, the quarks, and so it's a femtometer. It's almost as many steps down in scale as it is all the way up, the steps of 10 up to get to the size of the universe. So the problem is we think about 3 orders of magnitude bigger than ourselves and maybe 3 orders of magnitude smaller, and that's it. But there's loads more, but we're just not great at thinking about those. I like this. This is a friend of mine has made this. He was working for Google at the time, but now he's a professor. So he made the cosmic eye. There's various versions of this where you sort of zoom in and zoom out on these various scales. But the trick is that as humans, the physics that we understand, right? We throw a ball, that's the physics we know. We shoot a pool table, that's the physics we know. That's the scale that we're comfortable with. So on these scales, these scales, these scales, and the room scales, I'm good with that. And I could maybe go 1 smaller if I take a magnifying glass, and I can maybe go 1 bigger if you give me a vehicle of some sort, maybe 2. But that's what we're comfortable with. And then everything else is just big, and everything below that is just small and still unimaginably small. So when I'm talking about big and then still bigger and then still bigger, English doesn't really have the words for that, or we have a good concept of what those scales are. So when we embiggen, it's like, yeah, it's 10 times bigger than the last thing, which was already humongous, right? So Jupiter is humongous. The Earth is pretty big. I think that's sort of the largest human scale. If any of us has flown around the Earth, I haven't, but I know a couple of people who are frequent flyers. Maybe they go like, yes, I have a feeling how much that is. But that's sort of the largest scale in human concept. So anything bigger than that is just big. So how do we deal with that, right? Well, we can do that with the steps of 10, and so we can say like, well, this one's 10 times bigger than that. And so at least we can say 10 times bigger, 10 times bigger, 10 times bigger. There's a nice Indian legend where there was a philosopher who solved the problem for the king, and he was allowed to ask for his reward. The problem is that if you ask a king for something, you can't be too greedy because, well, they might get angry, but you can't lowball it either because they might be offended. So you have to sort of really thread the needle there. And so he came up with like a fun thing, and he said, all right, well, we've just played chess. I want 1 rice piece on the first square. Who's heard of this one? Okay, so there's 1 or 2 that is like, okay, so 2 rice pieces on the second one, 4 on the next one. Double the amount of rice every square. And this, there's 64 squares on a chess piece, on a chessboard. And so the king was like, well, sack of rice. Okay, fine. How bad do you think that gets, right? 1, 2, 4, 8, 16. The last square has 2 times 64, right? So it's 2 times 2 times 64 times 2 is 1, 8, and then this many zeros. Is 100 billion tons of rice. From Wikipedia in 2017, 210 million metric tons of rice was produced in the world. So the entire world will have to do, it's about 2 decades worth, 5 years worth of world rice production in 2017, modern rice production, not in India. So the king was the obvious solution, chop the man's head off, because he was way too smart for his own good. But you can get an idea. It's like you get up to large scales quickly if you use the multiplication point right there, right? So this means 10 to the power whatever. 10 to the power 2 means 100. 10 to the power 1, that's 110. That 1 times 10, that's 10. 10 to the power 9, for example, is a billion, but 10 to the power 10 is 10 billion. So this is how you can scale up quickly. Has anyone encountered this notation before? It's called scientific notation of if you need to encompass a lot of small numbers and large numbers. So this is how we write this down. I like this. I usually don't read the New Yorker, but this is kind of neat because it really encompasses how New Yorkers see the world. This is 9th Avenue, 10th Avenue, 11th Avenue is over there. Then you've got the Hudson River, all of Jersey, the rest of the country. There's Las Vegas, and then Japan. Basically, it's steps of 10, right? There's 1, 2 times that is basically that I'm at the Hudson River, and then 10 times that I'm at the other coast, right? So this is no big deal. This is almost as big of a deal. So doing this in steps of 10, so 1 meter, 10 meter, 100 meter, instead of steps of 1, right? If you're used to rulers, you think of 1, 2, 3, 4, 5, 6, 7, 8, 9, 12 inches, and then okay, and then the next foot happens. Now it's 1, 10, 100, 1,000, right? So we do steps of 10 this time. So drawing things like that I quite like, but that means that everything sort of gets squished together. So this is all of the solar system, even though this is 10 times further away than let's say Saturn, for example. So if you go above the Earth orbit, like it's 1 step from the satellites to the moon, even though it's 10 times further. And so that's how we express our distances, simply because they are so big. And it still doesn't give you a lot of intuition. It still just tells you it's 10 times further away, but if you have to put it in words, it's humongously far away. Come up with whatever superlative you want to do. So how do I actually measure things? How do I measure those distances? How do we know that? And so what we did is we bootstrapped our way out. And this is the part where I realized that not everybody had Baron von Munchausen as but you've all heard the phrase, pulling yourself up by your own bootstraps. Weir has heard of that phrase, right? You've all heard it. Where does that come from? Well, apparently there's a tall tale from the 17th century where it was a baron who said, like, oh yes, I got stuck in the mud with my horse, but don't worry, I pulled myself up by my own bootstraps. And it's meant as you can't do that, that's silly, but the phrase stuck. So we sort of did the same thing where we start with 1, we calibrate on 1 technique, and then sort of overlaps with the next one, and overlaps with the next one, and overlaps with the next one. We can do the first technique all the way to the last technique, but we sort of calibrate each one off each other as much as we can to get it as close as we can. Sort of the way that you can calibrate your odometer like going around a racetrack one time, because you know how long the racetrack is, because that's something you can walk with a little wheelie thing that counts foot, right? Have you seen those? They do this on campus, where they measure all of campus. There's a fun-looking class with like the little measuring tools. That's that will come again next on Thursday. So how do we measure this? Well, first thing is radar. Then we go from radar to parallax, and I'll talk about what parallax is, and then magnitude, standard stars, standard candles, and then redshift. So we have tools every time. And redshift is the redshift we learned during when we talked about the Doppler effect. So in our solar system, it's possible to bounce a radar or a laser off a nearby rock. This is absolutely a thing that you can do. In fact, that was one of the first things we did with the Apollo program. They actually put a little laser reflector on the moon, so you know that you can shoot at it and it comes back. This is the part where I realized that nobody's seeing Big Bang Theory again, but that is actually a plot point in one of the shows, right? Can you remember that they're on the roof with their laser and their telescope? They're bouncing off the laser off the moon. And so you can use a laser to sort of like send a blip over and then basically wait for the blip to come back and see how long that takes. You can do that with radar. You can literally send a big radar ping out and watch it come back. So the Apollo laser reflector, this is this little thingy that just left it there. And so if you have a powerful enough laser, you can bounce it off the surface of the moon, and specifically this laser reflector, and it will come back about 2 seconds later. So you can send a a series of dots, and then basically watch this series of dots come back about 2 seconds later. Because the moon is about a light second away, and it takes 1 second to get there, and 1 second to come back. Has any of you seen or heard any of the Apollo mission, like one small step for man, one giant thing for mankind? Yeah? And then have you, like, they say something, and then there's this really dramatic pause, and then Houston answers? The reason for that is that it took a second for their radio signal to get to Houston, and then a second for Houston to answer. Apparently this was one of the hardest things that the astronauts had to get used to. The fact that, no, they're not, just twiddling their thumbs. You're literally waiting for their answer to still come in. The distance is just long enough to notice the pause, but it's doable, right? You can have a real-time conversation. With the Arecibo radio telescope, this is in Puerto Rico, there's this big dome over here, and that you can send out a radar pulse basically out to the dome. It sends it out into space. You bounce it off the nearest rock, and you wait for that to come back. And so, for example, you can fix the astronomical unit, the distance between the sun and the Earth, which is going to be important in a little bit. That is our yardstick for stuff in the solar system, like 1 Earth-Sun distance. 2 Earth-Sun distances, that's roughly where Mars is. 70 is where, that's where Jupiter sits, or Saturn sits. And so, but you can wait long enough for that to come back, right? You can wait the hours that pulse comes, until that pulse comes back. I'm going to date myself here, but there's like a pretty neat James Bond before all the reboot, so to speak, and it happens like Arecibo pops out of a lake or whatever, but they're fighting up here, and the funnest part is actually watching that movie with your radio astronomy friends, because they go down a stairwell and turn left, and they go like, yeah, that door goes nowhere. That's literally a door on the side of the building, and it just goes straight down, but there's like another room there. It's like, there's no room there. It's really fun to watch that. Anyway, it is unfortunately no longer a telescope. One of those pylons cracked, and the whole thing fell down onto the telescope, so it's completely busted now. So the US doesn't have a radio telescope anymore in Puerto Rico, unfortunately. Meanwhile, in China, they do have a similar dish in a depression in the, so you find a good valley that sort of is dish-shaped, and then you build your dish in there. So that's sort of the biggest telescope that you can have. Trying to find like a human-scaled thing here to give you an idea of how big this is. I think that's a road. So that gives you an idea of like how big this thing is. It's 500 meters across. That doesn't tell anybody anything here. So it's sort of the size of campus. So you can make this really big if you have a nice big depression like this. Arecibo, let's do this. Let's show it in its full glory. This is 300 meters across. So yeah, this is basically about a block and a half, city block and a half. You can make these things really, really big, right? Since these are massive pylons, and you hoist the receiver in the middle. And so you can bounce a signal off, but you can imagine this gets tedious after a while, right? It takes 24 hours to get a signal to Voyager, to the Voyagers, for example. So that's 24 hours. And you have to sort of time it so that your radio telescope comes back into view when the pulses come back. So you can sort of measure things in our solar system, but the nearest star is 4 light years away. So you would send off your radar signal, and then you wait 8 years. None of us have that kind of patience. That's the nearest star. So if you want to do anything further than that, we're talking decades. We're talking like we're sending this really loud pulse, radar pulse, in one direction. All right, and now we're going to wait 50 years for this pulse to come back. Nobody's going to stick around for that. So how do we measure the distances to the nearby stars? And this is the trick that we use. So if you see people paint, have you seen people paint and they do this? They close one eye and they close the other eye. They're trying to check their perspective on their painting. Right, so if you do that, and here's the fun part, I get the whole room to do that. If you do this and you close one eye and you close the other eye, I don't shift, but your thumb goes back and forth, doesn't it? So let's try it all, right? Like I'm actually going to get you to put your thumb out, and close your one eye and close the other eye, or in some cases you like close both eyes, but you can see your thumb shift back and forth. So something nearby, your eye is sort of, your eyes correct for this automatically. Your cerebral cortex, your optical cortex is phenomenal at this. It corrects your vision as you go, but you have depth perception because you have two perspectives on nearby things. And so this depth perception is important because you have a baseline of about maybe 5 centimeters between your eyes. And so, and I know you've seen these people on campus. There is a class where you get the little measuring thing and you actually get to measure campus, because you measure the angle from A, you measure the angle from B, and you know this distance because that's a nice short distance. So you actually measure that out with a measuring tape. And you go like, okay, the angle to this tree is slightly different from A from B. I can work out what my distance is to that tree. I don't have to go over to the tree. I can measure it from two different angles. And you do this all the time. We are in fact predators, right? To first degree, our eyes up front. Any predator will have their eyes in front because they need to do the distance thing. They need to gauge the distance to the prey in order to jump on top of it or go, okay, it's close enough. If I sprint, I can catch it. Every predator needs that depth perception. If it's not a predator, they have their eyes on the side because they need 360 predator warning system. They don't need to do depth perception. So we do the same thing, but now we do this with two measuring devices, and we can actually measure the angle and estimate the distance. Again, we don't have a huge distance between our eyes, so it sort of doesn't work beyond a certain distance. Beyond 100 meters, it gets sketchy. But you can throw something over this distance. Somebody who throws better than me can throw something to the back row, and that person can catch it, because we both know how to gauge the distance to the thing. We know how big it is, but also our eyes automatically give us distance information because we do the parallax thing all the time. Okay, what would make a good baseline? Yes, I wasn't going to let you just sit there. Please get out your voting cards. What would make a good baseline for the distance to the stars? The distance between your eyes, the width of the planet Earth, the distance between the Earth and the Moon, or the distance between the Sun and the Earth? What would make a good way, so when I'm saying baseline, I mean this like distance between the two measuring points, right? What might make a good distance to the nearby stars? Voting in 1, voting in 2, voting in 3. Seeing majority D, so I'm going with it. Yes, we want to have as big of a baseline as possible, because if these things are really far away, we want to have as big as baseline to actually measure those angles. So that's exactly what we've been trying to do. Essentially, as soon as they realized that you couldn't do it with anything on Earth. And so you do it in July, and you do it in January, and you're trying to find the angle to the nearest star. And so this is a slightly better one. So you take you have your distance between the Sun and the Earth, and then you go to July and January, and then fixed with respect to the more distant stars, you should see that star move back and forth. That's parallax. We're looking at it in two different epochs, and it should have, if it's like this is our distance, this is our baseline, it should have a slightly different angle. Okay, what am I saying on this side here? The distance to the star in parsec, and a parsec, maybe you've heard about this because it features in the original Star Wars, right? You did it in 14 parsecs. Parsecs is a distance. So if you want to really pedantic about it, then you start talking about that. It's basically 3 and a bit light years. And that's a parallax angle in arc seconds. So I have to explain what an arc second is. You know what a degree is, right? A degree of angle, degree of, so you have 1 degree is 60 minutes of angle, and of that you take a 60th. That's an arc second. So I think your pinky at arm's length is about a degree. You take a 60th of a 60th of that. That is the angle that we're talking about. It's a tiny shift, and you can really only measure that if you have something like a camera. And so when photography was invented, the astronomers in the 19th century went, oh great, now we can actually measure even smaller angles. And they kept pushing and pushing. And they finally got some distances to some of the nearby stars and realized that they were literally light years away. But these things must be suns and even bigger than our sun and brighter than our sun. So here's an example. Alpha Centauri is famously the nearest visible star. And it has a value of 0.747 arc seconds. So it's not even a full arc second's worth of parallax. So is that distance, what is that distance in light years? Is that 1 parsec or is that even more than 1 parsec? It's a smaller angle. The distance is 1 over the parallax angle in arc seconds. So if I do 1 over 0.747, I end up with something that's even bigger than 1. So it's more than 1 parsec. It's more than those 3.27 light years. It's basically 4 and a bit. And so that's the nearest star, 4 light years. And you could just about measure that with photography. So if you want to know angles on the sky, I really like the fact that your pinky is about an arc as a degree on the sky. So usually when we're measuring things on the sky with our fist or with our our hands, essentially, we measure things in degrees. And now, that was the first thing that the actual distances were enormous. And so if you want to get an arc second, it's 1/3600, so 1 over 60 times 60. And so a arc second is basically a penny at 4 kilometers. It's really, really small. Measuring these things is incredibly hard. So doing that visually was impossible. You had to invent telescopes, and not only that, you had to invent photography to do it. So this mission has just ended, and we'll come back when we talk about the Milky Way, but this is called Gaia, and that was a European Space Agency mission where we're going to measure the distances out to about 1/3 of the Milky Way. So all these nearby stars we're going to actually measure a distance to. So now we do have that kind of accuracy where we had to measure that to 1/1,000,000th of an arc second. Completely dedicated space mission just to get distances to all the stars. It's been a raging success. It's been really fun to watch that come in, but it was hard. And this is the kind of thing you hopefully understand why. Angles are really hard to measure. It gets harder if you have to do them this small. Okay. So what we usually do is go, well, if these two things are brighter and that thing is fainter looking, it should be further away. You do this all the time. You do this in traffic at night, right? Most people's headlights are roughly the same brightness. So if I see the headlights closer by, angle, I see the angle distance, but I also, like, it's fainter, oh, it's further away. So a motorcycle, you don't get the angle information. You go like, oh, that motorcycle is still, a mile or two away because I'm just seeing this little small dot. Yeah? No? Do we measure that? Like, you do this sort of automatically when you're driving at night. So that gives us an apparent magnitude, how bright the object appears to us on Earth. That's our apparent magnitude. We have absolute magnitude, how bright a star actually is, its intrinsic brightness. So we sort of put it at a fixed distance. And so those are the two kinds of brightness. And this is how we measure apparent magnitude. So the naked, let's see, binocular limit, Pluto is plus 15. Okay, I want to be here, Venus. As soon as the sun sets, you basically get Venus, which is minus 4.4. The full moon is minus 12.6. And the sun is minus 26.7. And if I go fainter and fainter, the naked eye limit is plus 6, the binocular limit is plus 10, Pluto is plus 15, so you need a telescope to see it. Large telescopes, basically plus 21. Hubble can see to plus 30, James Webb can see to about plus 35. This is weird. The dimmer it is, the higher the number. I'm very sorry. This is how we got stuck with it. This is one of those things that somebody came up with literally 2,000 years ago, 2,000 plus years ago, and we haven't been able to change it since. So if with apparent magnitude, which one look brighter? So they look, the brighter it is, the lower the number. The dimmer it is, the higher the number. So which one look brighter, Sirius at minus 1.4 or Venus at minus 4.4? Voting 1, voting 2, voting 3. Fantastic. Yes. Parent magnitude, low m, so that's like lowercase m, and then we have minus 4.4, so lowest number, that is the brightest thing. Lower number, brighter object. Vega is, a magnitude of almost 0, and Teres is a magnitude of 1.06. Which one is brighter? Voting 1, voting 2, voting 3. The lowest number is the brightest one. All right. So the smaller negative number corresponds to brighter stars. Bigger positive numbers correspond to dimmer stars or objects. Why? Why do you do it this way? Just to annoy all the people in your 107 class? No. This is what happened. There's a Greek philosopher standing on the beach, sun is setting. He goes, first stars that I see are my magnitude 1 stars. The ones that I see after the sun has set a little more, those are my magnitude 2 stars. And as the sun sets more and my night gets darker and darker, I add more and more magnitudes until I get to 6. This guy was called Hipparchus, and one of our satellites was named after him. But yes, this is the reason that we have a magnitude system where the dimmer stars, the ones that I saw later in the evening, have a higher number. And we're still stuck with that because our eyes work as magnitude, so in steps of 10. Our eyes are actually logarithmic detectors. And so it's actually a pretty good scale, and it's pretty scientific, like it's pretty well calibrated. And so all the old maps are still in magnitudes that he originally came up with. All the old Arab maps, sky maps are all based on his magnitude scale. All the Greek maps have the magnitude scale. And then all the Renaissance ones have it, and all the, ever since then. So we're stuck with it because everything that everybody's done before has magnitudes, and this is the order that things go. If this is making your head hurt, you go like, okay, so brighter things, lower value. More negative means lower value means brighter object. If that makes your head hurt, it makes every professional astronomer's head hurt as well. We're just stuck with it. There you go. Okay, so why do stars in the night sky appear considerably different in brightness? A, the distance to stars is not all the same, and B, some stars are intrinsically brighter than others. They simply give off more light. Right? You can have big stars, and then it can look dim before you put them far away. So if these are all together, does this star look like that? And which one of these is giving off more light? Which star is actually giving off? So which star looks like it's giving off more light? This one might be closer, it might be bigger, it might be both. And that one might be maybe even the same kind of star, just 10 times further away. Right? Far away or intrinsically dimmer. So, how bright a star depends on how much light it releases, how its actual brightness or luminosity, and how far away it is. And so every time you go two times further away, it becomes 4 times dimmer. And I like this illustration because it actually shows if I have a star here, the amount of light that goes through this little square, if I go then 2 times further away, it now goes over 4 squares, so it's 4 times dimmer. And if the same light now it gets distributed over 9 squares, so it's 9 times dimmer if I go 3 times further away. It goes as the distance squared. Okay? So you lose it dims quickly, right? It goes as the inverse square law. It goes as the distance squared. It dims as 1 over the distance squared. And so it's sort of like you have to spread the same light over the same sphere, but now twice as big, 3 times as big. So that's called the inverse square law. And so you lose a lot of light quickly. And so how do we measure the luminosity of a star? So this is all the light that comes off, right? That's our luminosity, total output of light. And then over the distance, which is d here, 4 times pi d, like that's how I have to divide that over. That's the apparent that I'm getting at my little that I'm measuring it. So the range of stellar luminosities goes from literally a 10,000th of the sun to 1,000,000 times the brightness of our sun. So we have a huge range of stellar brightnesses already, right? It goes 4 orders of magnitude smaller than our sun and 6 orders of magnitude brighter than our sun. And so whatever I put in here, that's already a big range, and then all the distances are very varied. So, and then you have to keep in mind that the small or piddly luminosity stars are much more common than the larger and brighter ones. Okay, so if I then do a word problem where I say star A and star B both have the same luminosity, if star A has an apparent brightness that is 8 times less than star B, so it's dimmer, 8 times dimmer, what can we conclude about the distances to both stars? Star A is further away than star B by a factor greater than 3. Star A is further away than star B by a factor less than 3. Star B is further away than star A by a factor greater than 3. Star B is further away than star A by a factor less than 3. Voting 1, voting 2, voting 3. All right, I got sort of an even mix between A and B. So I'm going to do the following. I'm going to tell you to turn to your neighbor, and even if the two of you agree, explain to them why you think your answer is right. You've got about 90 seconds until I do my vote again. Let's try what you say. I think now. Voting in 1, voting in 2, wrap up the argument, and voting in 3. I got majority B this time. All right, 8 times, right? 8 times less bright than the other stars. So if I go back to here, if it's 3 times, it's 9 times dimmer. And so 3 or more is 9 or more times dimmer. If it's 8 times, it's somewhere between 4 times dimmer and 9 times dimmer. Closer to 9, but so it's in between here. So it's not quite 3 times further away. But can you imagine that that's how you can figure out how, if you go like, okay, these are the same kind of stars, and if you use spectroscopy, you can say like, they look the same. Their spectra look the same. So their peak and the brightness is the same. So the curves look the same. They're the same kind of star, but that one is 9 times dimmer than that one. Then I don't know what maybe the distance to that first star is, but I do know that the other one is 3 times further away. Right? You can get the relative distances this way. Yeah? So the only thing I need to do is figure out one nearby star. Like, which one can I actually get a parallax distance to? So as soon as you have one, maybe a few more, then I can get like, okay, that's this type of star. I know its distance, and that means any other star that I can find that's the same kind, I can get its relative distance by just the brightness. I don't have to measure the parallax to every single one of them, just a few nearby ones. And so that's how we solve the problem. But then with Gaia, we now actually get distance to more. Okay, so which one looks brighter from Earth? We have Rigel and Spica, 2 lovely Arab names of some nearby stars. Rigel has a magnitude of -0.01, and Spica has an apparent magnitude of +1. Which one of these is the brightest from Earth? Voting in 1, voting in 2, and everybody has the right answer up already. Thank you very much. It is Rigel. All right, so Rigel's the brightest one, but it turns out that Spica actually gives like 1,000 times more light off than Rigel. So if Spica is giving off more light, why would it appear dimmer here on Earth? Because Spica is so much further away. And so you need to know both the distance and the intrinsic magnitude, the absolute magnitude. So if I put any star at a fictitious distance of 10 parsecs away, so how bright would it be if I put this star 10 parsecs away? Then I have an apparent, then the magnitude that I then would measure is the absolute magnitude. So where I fix the distance at 10 parsecs. And so note the capital letter M there. So if I talk about absolute magnitudes, intrinsic brightness, it's capital M. And so from that we can get distances, right? If I know the intrinsic absolute magnitude of the star, and I measure the apparent magnitude, I have that, between that relation, I get a distance between those two. I get the distance. And so the distance is 10 to the power, and then the apparent minus the absolute magnitude plus 5, and the whole thing divided by 5. This is an expression how to get distances if you just have luminosities and you know what the type of star is. So you already know it, you intrinsically know how intrinsically bright the absolute magnitude of a star is. Okay, does this concept ring okay to you all? So absolute magnitude, if I figure out how bright this should be at 10 parsec, like that is my intrinsic brightness of the star. So that's the absolute magnitude we're using. I get distances out of that. So if the apparent magnitude of a star is greater than the star's absolute magnitude, what can we conclude about the distance of the star? So the star is further away than 10 parsecs, the star is exactly 10 parsecs, the star is closer than 10 parsecs. So the apparent magnitude is greater than the absolute magnitude. It's a greater value. Volume 1, volume 2, and volume 3. I get just enough. Some people are not holding up their voting cards. All right, I'm getting a little bit of the rate. Okay, let's, the star is, like the apparent magnitude of the star is greater, so it is a greater value, it is a dimmer value than the apparent, the absolute magnitude. The absolute magnitude we measure at 10 parsec. Nobody had B, which is great, right? It means that you know that there's a discrepancy. And so if it's dimmer than the absolute magnitude, because it's a greater value, it must be. Okay, I'm going to go walk around, turn to your neighbor. Even if the two of you agree, explain to them why you think you're right. One, voting 2, voting 3. Oh, you all convinced each other. This is fantastic. Yes, it's dimmer. Dimmer things are further away. There we go. It's really easy to trick yourself. And so this is the kind of math challenge we have, like which star is the brightest from Earth, which star is the brightest, and which star is the furthest. So if I have an absolute and apparent magnitude, the absolute magnitude of the sun is 4.8. So if I put the whole thing at 10 parsecs, much further away, it's 4.8 absolute magnitude. If I look at it, it's minus 26. It's really bright. Sirius, the absolute magnitude is 1.4, much lower than the sun, so it's brighter. The apparent magnitude is minus 4.6. It's not as bright as the sun, thankfully. And then Betelgeuse is minus 5.6, and then the apparent magnitude is 0.5. All right, so of these, which star looks the brightest from Earth? The sun. That's the easy one, right? Okay, which one is the brightest star intrinsically? Betelgeuse. Nobody say that 3 times fast. And which star is therefore the furthest? That's the last one that is the trickiest one, right? So which one's the furthest from us? Betelgeuse again, right? So, trick is the difference between these numbers. That's the one that we're looking for. The biggest difference between those means that we have the biggest distance. You already knew that the sun wasn't the greatest distance from the Earth because we'd be in real trouble in that case. All right, so Um, and we already did that one. So if the apparent magnitude is exactly as the absolute magnitude distance is 10 parsec, if the apparent magnitude is smaller, then the absolute magnitude distance is less than 10 parsec. If it's greater than, that's most of the cases, but most stuff is more than 10 parsecs away. So we have a group work on absolute apparent magnitude. Magnitudes are tricky. I completely sympathize, and I still have people, I'm one of them who goes, absolute apparent magnitude, which way now? I have a little file that helps me remember this stuff. And because I have trouble remembering which way these equations go, they will definitely be part of the exam, meaning that I give you the actual equations, you just have to figure it out yourself. There is a sort of group work for everybody to work on the apparent and absolute magnitudes. Try not to hand them all out here at the beginning. About 8 minutes for this. It's reasoning mostly. And then we can go on to the next parts of the distance ladder. Let's see how far we get today. I mean, I have a little bit of spare on Thursday, but we definitely want to show distances using the planetarium. If anybody has spares, then please let me know. Right, remember, this is a group effort, right? So make sure that you team up with somebody and reason yourself way out. You're perfectly welcome to keep one of the worksheets, but I want to see maybe 2 names or more at the top. All right? the absolute magnitude. So this is the absolute magnitudes, and yeah, you're writing like absolute magnitudes. And then, but then it's like energy. The lower the magnitude, the brighter the image is. The number of people that got mad at me about the whole magnitude thing, I completely understand, is not zero. And I get it. I have a little file that says magnitudes what now, because I have to remind myself. It's counterintuitive. I'm sorry about that. This is what we're stuck with. The more negative is right, intrinsically, is the absolute magnitude. Intrinsic So this is the part where it's like, am I asking how bright it is? Am I asking about the apparent magnitude? This is my evilest assignment because you have to go like, oh, it's the other way around. Yes, I've done that. Don't worry about it. We're all done it.
It would just be based on how big the absolute magnitude is just to the right, so B is 6 so it would just be like BA, just the numbers.
How are we doing? Still working on it? It's a tricky one, to be honest. Yes? What's the lowest one? Yeah. So that's the intrinsic gain. All the magnitudes are right. Okay. Those equations you'll get from them. Right? So I have to like what was the negative again? I don't trust my memory with these, so like, why would I trust your memory? It's like I just put them on the paper, the better. The main thing that we're all remembering is, which is good, that if it's a lower value, the thing is brighter. So you see a apparent magnitude, a lower value, it appears lower value of absolute magnitude is intrinsic, absolutely to as it appears to me. Yeah. C is the intrinsically brightest. I was taking a little longer. for the magnitude value, the brighter it is. It's that reverse thing. Like this whole exercise is about, oh, the lower value means bright. If it's apparently or absolute is intrinsic. So you go from the greatest value out to the least, but then the rank after rank is either a reasoning arm or a question arm. I don't know. Is that a question or was that just pointing at the ceiling? All right, cool. Okay, I think everybody's sort of. So, why am I putting you through this? Well, two things. One, every star map will have this little number sitting next to it. And it'll be like, this is how bright it appears. And then also, we'll see these numbers appear when we talk about color magnitude diagram. Again, the y-axis is the magnitude, it's the intrinsic brightness, but it'll be marked with absolute magnitude. So, how much brightness they appear at 10%. This is a neat little thing where you can figure out, as soon as you have this, as soon as I know what kind of star I'm dealing with, I can go measure distances. And there is another trick that I have, which is that, as it turns out, if you have a pulsing star, that tells me how big this thing is. Its period actually tells me how bright it is. And so that's what the next thing I want to talk about. And I have 15 minutes, so I am going to do it. Because that is sort of like, that became the next trick that we used, standard candles. And so the term that I want you to understand is a standard candle means, oh, I know how bright that is. You watch a candle somewhere, you see a little flickering candle in the distance, you have a good idea how far that candle is. Because a candle flame is usually the same brightness. Doesn't really matter if it's a big fat candle or a small one, it's that little wick and that little flame. It's usually the same brightness, right? So you've done this. If you're in a church and there's just a couple of candles around, you know that that candle is at the back of the church and this one's closer by. Okay, so that's why we call them standard candles, because we know intrinsically how bright they are. And so an example are the Cepheid variable stars and supernova of a certain type. Cepheids are the first ones that I'm going to talk about, but they come down to, if I know how bright it is, and I can then actually figure out what distances they are, or if I had something that was the right size, that was always the same size, I would use it as the standard ruler. Unfortunately, there's nothing in the universe that we can observe easily that is always the same size. Galaxies range in about 6 orders of magnitude in size. Stars range in 10 orders of magnitude in brightness. Right? Nothing is always the same size, unfortunately. But there are a few things that are always the same brightness, or we can figure out what their intrinsic brightness is. So those are our standard stars. Cepheids, and we'll talk more about them on Thursday, they are pulsating stars, so they become brighter, and they become dimmer, and they become brighter, and they become dimmer. And their period is directly related to their luminosity. You can sort of realize how that goes, because not everybody here is maybe a musician, but maybe you've all played xylophone when you were little kids, yes? The low tone is a bigger bar. Remember that part? You hit that, you get the doom, and the small bar was like ding. Do you remember? No? Okay. Right. Basically, if you have a big thing, it takes a while to pulse. If you have a smaller thing, it can do faster pulses. So a faster pulsing one is a smaller, dimmer star. So the period in days is related to the absolute magnitude, right? Basically, longer period means bigger star, means brighter star. And so Cepheids are very particular, very regular, very regulated star, basically. It always gets brighter and then dims, brighter and dims. Very conveniently, it's about a week, so it's not like you have to spend months looking at this thing either. So you can look at this thing, go dimmer and brighter, see what the period is, and then measure, and you've got the absolute magnitude. So I have an intrinsic distance, I have a distance measurement. And that is, and this is not a rule break of the dead white guy rule, this is not a dead white bright guy, plus he's rocking a really cool dress. This is Henrietta Leavitt, and she worked as a computer at Harvard and discovered this period luminosity relation for Cepheid variable stars, completely on her own. So we call this now the Leavitt law. And she found this out because she was studying the brightness of stars in a nearby galaxy, the Large Magellanic Cloud, or the Large Milky Cloud, if you want to call it. And so there are variable stars dotted around here, but they're all sort of the same distance. That galaxy's all, they're all in that same galaxy. They're not, massive distances in there. This thing is all roughly at the same distance. And so she found the variability in days, and then their intrinsic luminosity, the luminosity that she found, and she noticed that there was a straight line there. So it's like, okay, as soon as I have this distance, I know the intrinsic luminosity, I can calibrate this. So we have ones from the Milky Way and the ones from the LHC, so we measured the ones here in the Milky Way, and we found their parallax, so we got their distances, and then we got their absolute luminosities, and we calibrated the relations to the Magellanic Cloud, and that got us a distance to the nearest galaxy. Aha! So a trick that I'm using on stars gets me the first nearby galaxy. So at least I got a distance to that. And so in order to use Cepheids to get a distance, you measure both the dimmest and the brightest luminosity, calculate the average, and call that the apparent magnitude m. Calculate the absolute magnitude from the period using the following formula, right? So the absolute luminosity is minus 2.8 times log 10. Is everybody familiar with taking the log of something? Okay. If anybody isn't, I'm happy to give you a little sidebar on like what to do with your calculator in order to get that. We all have a fantastic scientific calculator. It's this thing sideways. The calculator app put sideways, and suddenly you can move all those things. So you take the log 10 of the period in days, right? So you have like a 5-day, you take the log of that, so you get 0.2 times that minus 2.78 minus 3.5, and that gives you the absolute magnitude. Notice that this is going to get negative, right? It is a pretty bright star. That's also really helpful. These things are not only pulsating in a very regulated way, they are also nice and bright, so I can see them in the next, or basically, the Leavitt could see them in the next galaxy over. And so then we get the distance equation. We have the apparent one, we have the absolute one. We measure it, we get the distance in parsec. We want it in light years, which is multiplied by 3. So if I find Cepheid variable somewhere, I can get distance to it. So as long as I can find the Cepheid variable, I can get the distance to it. And I can do this in a couple of nearby galaxies. Like if I have a good telescope, I can actually find the little star in there pulsating up there. Now, I'm going to tell you something about how NASA works. If NASA gets a mission together, it takes a decade at least, because we define the thing that is the absolute win-all science case. There are things we want to do with it. There's things we're going to do with it. But this is the mission success criteria, right? So you land on Mars and you have a little rover. What's its mission success? First rover, it was basically, it didn't break. That's your mission success. Cool, okay. What's the other mission success? It goes in and measures actual, 5 measurements of soil. So for the Hubble Space Telescope, a 35-year-old telescope now at this point, so you all grew up with Hubble pictures are just a thing. But it was at some point a concept, it was at some point a plan, it was at some point a mission for NASA to run, and its primary mission was measure the distance to the nearest 2 dozen galaxies. Because we didn't know how far these things worked. We didn't know that to a good distance, a good accuracy. And the thing it was supposed to do is look at nearby galaxies and look for something like a Cepheid. So Henrietta Leavitt's trick applied now with the best telescope we can build on the nearest 2 dozen galaxies, so we can know how the nearby neighborhood looks. If we got that and the telescope broke, NASA would call it a success. Right? This is the part where we go like, okay, if you hit mission success with your telescope, if you hit mission success with your mission, and that is like, okay, you've done that part, and afterwards it breaks, then NASA calls it a successful mission. If you don't get, you don't get that one, you're basically looking at a failed mission. If you've done that and you go like, oh, but the telescope works just fine, you're like, great, let's do the 500 other things that we thought of we could do with the Hubble Space Telescope. We totally have, right? Every time that there's a new call out, and the deadline is in April, and every astronomer on Earth will write a little essay saying, I want to do this with it. And you kind of figure after 35 years, we've sort of done them all, right? We've done all our ideas that we can do with the Hubble Space Telescope. Nowhere near. It's a 10 times oversubscription, meaning that you have to beat 9 other astronomers in order to get your idea worked out on this 35-year-old telescope. Who here drives a car that's 35 years old? Okay. Not many of you, because cars don't last that long typically. We're talking something that's in space. It's only had a service mission 5 times, so it's basically got its oil changed 5 times, and that's it. It's still trucking, and it will probably still be trucking 5 years from now. And we can still think of so many new things to do. But it was already a success in 1998. We were all born, or not even yet, when we measured the distance to the nearest stars. Mission success for Hubble was already achieved at that point. We've been doing all kinds of cool science since, but that's what it was launched to do. So we always figure out, like, this is the bar you need to cross with your science mission. That was the primary mission. It was called the Key Project. And so, like, this is the thing that better work. And let's see if we can accomplish it. And so the neat thing is, so these are these really old pictures you can see because they're grainy and full of pixels, and we actually put better cameras on Hubble later, but you can see that it got dimmer and brighter. So we found Cepheids in all of these different galaxies. We'll work on the Cepheid example on Thursday. So Cepheids can be used as long as you can find them, and as long as you can tell, like, you can go back, because April, May 4th, May 9th, May 16th, you have to go back every day or so in order to get that period. Or if you do this with, more recently, you of course make a GIF out of it, and so you can watch this thing get brighter and dimmer as we observe. So Andromeda is our nearest neighbor. So I'll talk about this some more pick this back up on Thursday when we talk about distances, but this was the last thing that we know when we use Cepheids, and the other one that we use are supernovae. The Cepheids one is just the Key Project. Please leave your group work on the technical station, and we'll talk more about this on Thursday. Any questions? Come down here after the camera. All right, otherwise I'll see you on Thursday. Thanks for coming.
Is this yours? Oh. It was just on the ground back there.
Okay. Where do we?
Just back here.
Because I was gonna play ball with y'all, but like I started walking on my foot, and I was like,
Oh yeah, like you would have said, like, did you try to? I would rather. You're right, bro.
This is why I it's perfect. Anyway, so yes, and now we're all.
Like up there.
Plug those in.
Hey, what's the worst ones? That's the worst kind of work. You get more project.
See, I was all good with like the writers all
Please, whatever, what, oh, you know, is that, okay, if you have an issue with it, let me know, because I like the fact that it's, I can track everybody in Blackboard. I found that experience is really the stuff. So it's like this way, it's easy for me to create a way where it's easy for me to keep tabs with everybody. But if you're having a technical issue, it's hey, Rafi, what's up? I'm coming up there. So, good job for recording.
I apologize, like I just, yeah, came here
What's up?
without any